everyone. Thank you guys for coming. My name is Peng from Tsinghua University in China. Today I'm going to be talking about titanium oxide and shrink-induced tunable graphene composites based on nano self-assembly for biosensors. First, I want to talk about graphene and graphene composites, and then talk about how to make graphene composites tunable and how to control its properties, such as wetting ability, mechanical properties, electrical properties, and so on. And the performance of the sensor, biosensor, based on these new graphene components can also be tunable. The last part is conclusion. Graphene is two-dimensional honeycomb crystal of sp2 bonded carbon atoms. It has a lot of amazing properties. For example, its carrier mobility, its extremely high carrier mobility and thermal conductivity make the promising candidate for the next generation electrical devices or sensors. And its super high Young's modulus and breaking strength make graphene a good material for NEMS, nano electromechanical systems. This SEM image on the right top shows the single crystalline graphene flakes synthesis by chemical vapor deposition method on copper foil in our group. And its Raman spectrum demonstrates that the graphene is a monolayer. It doesn't have a prominent D peak in the spectrum, so it indicates the graphene has very low defect. It's close to intrinsic graphene. So besides intrinsic graphene, people also try to integrate the graphene nanoplatelets with other materials to get advanced multifunctional devices, structures, such as a layer-by-layer self-assembly graphene. It has a layer of PDDA polymer at the bottom, which is positively charged. It has a graphene nanoplatelets, which is negatively charged, another layer of PDDA, and another layer of graphene, this sandwich structure. The SEM image on the right top shows clearly this layer-by-layer graphene film. The graphene nanoplatelets is about 150 nanometers in size. And this Raman spectrum has prominent D peak here because the edge of the graphene nanoplatelets introduce a lot of defects. Most of the graphene components reported so far are not tunable because of their synthesis process or because of their fixed structures. So we try to use shape memory polymer PO and titanium oxide nanoparticles to derive a tunable and controllable graphene components, even after the synthesis process. This is how we did it. First, a silicon mold is placed on PO polymer, and we use hot embossing to make patterns, to transfer the patterns from the silicon onto the PO. And we used sandpaper polishing to remove those patterns. Next, we deposit layer-by-layer graphene on the surface of PO polymer instead of a regular layer-by-layer graphene that I've just mentioned previously. We add titanium oxide nanoparticles in the center of this sandwich structure because it can change and tune the properties of these graphene components. And finally, the PO polymer with graphene was heated to desired temperature for shrink. The polymer starts to show obvious shrinkage when the temperature is over about 100 degrees Celsius. Because it's called shape memory polymer, it intends to restore to its original shape. So you can imagine that as a result, the high aspect ratio patterns can be formed on this surface PO polymer. So we can use PO polymer to change and tune the shape of graphene components in this way. This is the SEM of the microchannel arrays on PO polymer right after hot embossing and before sandpaper polishing and heat shrink. And this is the same sample after heat shrink. We can see some microchannels with high aspect ratios on PO surface. With the PO polymer, we can do something interesting. For example, we can change those dot arrays on the mold into the needle shape patterns on PO polymer after heat shrink. We can also shrink the coin into a much smaller size. After shrinkage, the PO polymer, the lateral size of the polymer reduced to about 1/3 of its original size. But the depth of the patterns on PO polymer increased to about 6 to 8 times. So PO polymer is very suitable for high aspect ratio nanostructures, according to our observation. The titanium oxide nanoparticles we use are derived from the following chemical reaction. The titanium nanoparticles is about 150 to 200 in diameter. The water contact angle on titanium oxide coated surface is almost 0 degree, indicating super hydrophilic. On the other hand, the contact angle on silicon oxide surface is about 50 degree, so it's relatively hydrophobic. The layer-by-layer graphene film with different thickness of titanium oxide layer will have different colors on silicon oxide surface and different water contact angle. For example, if we increase the thickness of titanium oxide layer from 10 to 100 nanometers, the water contact angle of this graphene film will reduce to about 20 to 10 degree. And after the heat shrink, the water contact angle, you can see that it increases dramatically because of those nanostructures. So the wettability of these new graphene composites can be tuned by the thickness of titanium oxide layer and the shrink temperature. And we can tune the graphene composites from hydrophilic to hydrophobic. Besides that, the electrical and the mechanical properties of these graphene composites can also be tuned and controlled. When the material acts as the functional material of the electrical device, its conductance is very important for the performance. The titanium oxide nanoparticle conductance is smaller than graphene nanoplatelets. So when we added titanium oxide in the center of the film, it reduced the connection of adjacent graphene nanoplatelets. So as a result, the conductance of the film decreases. On the other hand, the 3D structure after heat shrink can introduce small connections between the graphene nanoplatelets. So as a result, it can increase the conductance. Therefore, the resistance of these graphene components can be changed and tuned by the titanium oxide layer thickness and the heat shrink temperature. We use atomic force microscope microcantilever to indent the surface of layer-by-layer graphene components to study its mechanical properties. And from this picture, you can see that when the thickness of titanium oxide layer increases, the slope of this retraction force curve of AFM also it reduces. So the layer-by-layer graphene, that indicates the graphene film has smaller stiffness. So the stiffness of these new components can also be changed by adding titanium oxide nanoparticles. And then we further investigate the properties of these new graphene components in the application of biosensing. We immobilized the antibodies on the surface of the layer-by-layer graphene film, and after it absorbs certain types of antigens or tumor markers, in our case, the carrier density and carrier mobility of this graphene will change. So it can result in different resistance values of the whole film. From the resistance value shift, we are able to know the concentration of the tumor markers. This kind of label-free biosensor doesn't need a time-consuming labeling process or sophisticated optical detection system, and it's very low cost. We use it to detect the lung cancer tumor markers. Lung cancer has the highest death rate in China so far. According to the paper published, there are 3 important lung cancer tumor markers, EN01, AXA2, VEGF. We detect them and measure the layer-by-layer graphene film resistance shift according to the different concentrations of those tumor markers. This is our experimental result. We can see from picture that when the concentration of ANXA2 antigen increases, the resistance shift of the graphene film also increases. The layer-by-layer graphene's response is this black curve, and the layer-by-layer graphene after heat shrink is this pink curve. We can see clearly that after heat shrink, our sensor, the signal increases dramatically, or the resistance shift increases. I think this is because the heat shrink introduced small surface, enlarges the surface area of the film, and it's easier for us to detect the antigen with low concentration in this way. However, after adding the titanium oxide nanoparticles in the film, we find that the signal of the sensor decreases a lot, especially in this low concentration region. So it's harder for us to detect the antigen with low concentration in this way. We think because it's the scattering of the titanium oxide reduce the carrier mobility of the graphene nanoplatelets. But we find another interesting phenomenon. The signal doesn't reduce too much in high concentration. We still need to study the reason, find out the reason. But as a result, the slope of this curve increases. So from the definition of sensitivity, our sensor has higher sensitivity after adding titanium oxide nanoparticles as a result. So if we combine the heat shrink and titanium oxide layer together, the green curve, our sensor will have good sensitivity, and it also can be used to detect the antigen with low concentration. In a nutshell, the heat shrink can increase the signal of the sensor, and titanium oxide nanoparticle can increase the sensitivity of the sensor. Conclusion. We developed a simple and low-cost approach to use shape memory polymer PO and titanium oxide nanoparticles to derive a tunable and controllable graphene components. And the film's wettability, electrical, and mechanical properties can be tuned and controlled. And the performance of the sensor based on these new graphene components can also be tuned. And the tunable graphene components is expected to offer more controllable and flexible applications in chemical, biological detection and microfluidic with a simple and a low-cost strategy. We acknowledge the system of fabrication and characterization from Minnesota Nano Center and the characterization facility at the University of Minnesota. And thanks for your attention.